Okay, so for the next part of this example, we're going to use a capital of 2 instead of a capital of 1 to see what happens to our short-term costs is we expand the fixed input. So we have a higher level of capital here, and we want to see how that affects our short-term cost curves. So again, we're going to start by finding our short-run total cost curve, and then we can take the derivative to get marginal cost and divide by Q to get average total cost. So I'm just going to take this equation and plug in my new capital along with my input prices to get my short run total cost equation. So I've got 25Q squared divided by 2,500 times Q plus 100 times 2. So that's giving me Q squared over 200 plus 200. Let's compare that to our original short-term total cost equation. It was Q squared over 100 plus 100. And so you'll see that both terms have changed. The fixed cost term has increased. So we have an increase in the fixed cost from 100 to 200. That makes sense because we have more capital now. So our costs from capital have increased. And notice that the marginal cost has decreased. The marginal cost has decreased. It's become flatter than it was before. So it's lower at any level of production. And that's because each unit of labor now has more capital to work with. So each unit of labor will be more productive, and therefore the marginal cost as we add more labor is smaller since we have the higher level of capital. All right, and we'll be able to see that if we write out our marginal cost equation. So again, you could plug the numbers into those master equations, but I think it's simpler just to take the derivative here of our new, very much simpler total cost function. So that's going to be 2 times Q over 200, which is Q over 100. And again, you can see comparing that to our old marginal cost equation, Q over 50, you've got a flatter slope. And then for our average total cost, we would just divide the short-term total cost equation by Q. So I get Q over 200 plus 200 over Q. Great. So now what we're going to do is plot these on the same graph that we were using before to see how they shift as we expand capital. And so let's plug in these same numbers to our total cost equation here. At 0, our fixed cost is 200. At 10, I've got 200.5. At 100, I get 250. And at 200, that's going to give me 400. So I can plot that on the graph up here. 0, my fixed cost has increased to 200. At 100, I go up to 250, and at 200, I am at 400. So again, you can see we started a higher fixed cost, but the slope is a bit flatter because each unit of labor has more capital to work with, so my marginal product of labor is increasing. All right, so let's give that a, we'll use this blue color here to show what's happening to our total cost curve. All right. Then for marginal cost, okay, I can plug in these quantities. I get again, it starts at 0. 10 is going to be 1. This is 1 and 2. Okay, so I go 0, 1, and 2. My marginal cost equation is going to look something like this. And I'll label that at 2. And again, I'm just going to highlight that so we can notice some patterns here. Okay, now what's happening to our average total cost? Average total cost, well, it's going to start out higher than before, right? Because I'm starting out with a higher kind of upfront fixed cost than I was before. Again, it's not really defined at 0, so we've got that 10 to help us out with this. So if I plug in 10, I get 20.05, which you notice is higher than the 10.1 we had before. At 100, it's going to be 2.5, and at 200, it's going to be 1 plus 1, so that's 2. Again, you can see that in this example, we're plotting this point where the two curves intersect, but normally I will have you solve for that point instead. So starting out really high. So that's gonna be my average total cost and a quantity of 2. Okay, all right, let's make it green. And again, you can see here that the two curves intersect at the minimum, and in this case, the minimum average total cost is at a quantity of 200. We can solve for that. Let's practice using the second method for solving for the minimum average total cost. So we'll take the derivative of average total cost with respect to quantity and then set that equal to 0. So we got 1 over 200 minus, because I got that q to the negative 1 there, minus 200 over q squared equals 0. And you could rewrite that as 200 times q to the negative 1 if that's helpful for you to take the derivative. Okay, so I'm going to move that term to the other side, and then I've got these two fractions. Again, the easiest thing to do is to cross multiply, so I end up with q squared equals 200 squared, so q is going to be 200, which we knew already, but this shows you how to use the method where we take the derivative of average total cost and set it equal to 0. So this is, again, this interpretation, this is the level of production that minimizes average total cost, or the cost per unit, when our capital is fixed at 2.